Well, we're going to take a complete turn today and we're going to do something very, very different. Now, students usually love this section because this section is very straightforward. We're talking about exponents. We're going to have a few rules. You're going to need to memorize the rules or at least understand how the rules work, and then you'll apply those rules, but it's really straightforward. And the problems are short. They're really short, they're really quick, and most people think they're really easy. So let's talk about exponents and a few of the features of exponents that we're going to need to know. An exponent is something I'm sure you guys are all familiar with. You might see something like this. How about 5 to the third? In this example, 5 is a base. So this definition right here, it's the thing that's raised to the exponent. And 3 is the exponent itself. So the pieces of this expression have different names. We've got our base, which is 5, and our exponent, which is 3. Well, what does this mean? This means take your base and multiply it together 3 times. So 5 to the third power, or 5 to the exponent of 3, means take 5 and multiply it together 3 times. 5 times 5 times 5 is 125. So we could actually calculate a number for this. Now, a lot of times when we're dealing with exponents, we don't just have numbers. Sometimes we'll have variables, like in example 1. In example 1, we want to label all of the pieces of this problem. We have x to the 4th. So I could rewrite this kind of with color coding. X is a base, and 4 is the exponent. So what this means is take x and multiply it to itself 4 times. X times x times x times x. But it's annoying and hard to write that out all the time. So we came up with this little shortcut notation that just means multiply it together this many times. So in these examples, we want to label our coefficients, our bases, and our exponents. So we already mentioned that x is a base and 4 is an exponent. So I'm going to label them by color coding them. You can draw arrows or circle things and label them that way if you'd like. That's all that there is to it to this example. Question 2 is a little trickier. There is a really, really, really important feature of exponents that you have to get into your brains. Exponents only affect the base it is directly touching. So in order for an exponent to affect something, it has to be directly touching it. So let's look at this second example. 2 is obviously an exponent. The thing that the 2 is directly touching is the x. It is not touching the 5. So the 5 is separate. The x is a base, and the 2 is the exponent on the base. But 5 is not part of the base or the exponent. We call that a coefficient. So I'm going to label 5 as a coefficient. X is our base, and 2 is our exponent. So these are hopefully feeling pretty straightforward by now. In our next example, 3, we have multiple exponents with multiple bases. So you can have many different bases and many different exponents in the same term. For instance, here we've got a base of 4 with an exponent of 2. We have a base of x with an exponent of 3. And we have a base of y with no exponent. But don't let that fool you. Everything has an exponent. We can write one in. You can always put the number 1 there. Even if it's not written on your variable, you can always write it as like y to the first power. So it's always there, we just don't write it. Okay, in the fourth example, this one's a bit tricky too. Obviously, we have an exponent. And our rule is that exponents affect whatever they are directly touching. What is this exponent directly touching? It's not the a, it's the parenthesis. That exponent is directly touching this parenthesis. But parentheses come in pairs. So our base is actually everything from here to here. Because our exponent is touching the parenthesis, that whole parenthetical expression is the base. So we would say that the base is 3a, and we could even say it's 3a in parentheses is our base, and then 2 is our exponent. I just realized I forgot to label the exponents and the bases in the previous example, but all the red things are exponents, all the green things are bases. So one thing I want to point out about number 4, if you are actually squaring this out, if you are going to do this as if it were a problem, all we're doing right now is labeling. But if you wanted to really simplify this, to square something means to multiply it to itself. So if we wanted to multiply this out, to square 3a, we would just need to multiply it to itself, parentheses and all. We write it all. Everything that's part of the base, we just rewrite it. So it would be written like this, and you could rewrite that 3 times 3 times a, and then you could simplify from there. We'll get into problems like that in just a minute. I just wanted to point out this notation involving the parentheses. We're going to move on to a real rule here. We do in algebra, we do a lot of things like adding and subtracting terms, and often those terms have bases and exponents in them. So we need to talk about the rules we use when we add things together. When we are adding and subtracting, the rule we use is combining like terms. And this should not be new to you. You've done this all year long. You probably did this last year and the year before and the year before, every time you've ever taken an algebra class. Combining like terms is one of our basic rules that you already know. The rule is you add the coefficients together. The exponents and the bases do not change. So let's take this first example. We want to combine like terms together. So first of all, we have to identify which of these are like terms. Terms are alike if they have the same bases and the same exponents, and they have to match exactly. The bases and the exponents have to match exactly. So I've got a couple of terms here with an x squared in each of them. That's the same base and the same exponent. The coefficients in the front don't match, but that's okay. We don't have to have matching coefficients. We just have to have matching bases and matching exponents. The rule is we add the coefficients together, but our exponents don't change. So we're going to add together. Actually, let's rewrite this. So I'll rewrite it so that we've got 3x squared plus x squared plus 17x minus 25x. So all I've done here is I've rewritten this in an order where my terms are grouped into like terms. And I color-coded mine. You don't need to do that, but I find it visually useful. So my 3x squared and my x squared are like terms because they have the same bases, the same exponents, and when we add them together, we add the coefficient in the front. Notice there isn't a coefficient in front of the x squared, so we can put a 1 there. So the two numbers, the two coefficients are 3, wow, that was unfortunate, are 3 and 1. So when we add those two coefficients together, we get 4x squared. Notice the x's didn't change, the squared didn't change, just the coefficients got added together. Now let's look at the green. The two green terms are like terms because they both have an x to the first power. We didn't write the 1 in, but they're there. So these are both x to the first, x to the first. Those are like terms because they have the same base and they have the same exponent. So our rule is we just need to add the coefficient in the front. Well, positive 17 minus 25 will give us a negative 8. So we'll have a minus 8x. It's an x to the first, but we don't have to write the 1. So notice the variable, the base, the exponent didn't change, just the coefficient changed. Did everybody follow that? Make sense? Let's do a few more examples, but we'll go a little more quickly since I know you're already familiar with this. In example 2, we've got a couple of like terms in our y squared, and then we've got one 4y that doesn't have anything it can combine with because it doesn't have any other additional like terms. So we're just going to add together the coefficient negative 6 with the coefficient positive 6. Well, negative 6 plus positive 6 is 0. So that becomes a 0 y squared. And then we have this plus 4y that doesn't have anything it can combine with. We don't even need to write the 0 y squared because 0 times anything just disappears. So this is all gone. And then all we're left with is a positive 4y. So I'm going to even erase that plus. This is our answer, 4y. One thing I see students do a lot, if you have two things that are exactly alike except for their sign and they're being added together, you have a positive 6y squared and a negative 6y squared. I've seen students just cross these off. That's perfectly fine. That is a very acceptable way of showing your work on this problem. So you don't have to write out all the steps that I just wrote out. You can just cross them off to indicate to me that you know that these cancel. All right, and problem 3, this problem is just here to demonstrate to you that it doesn't matter how complicated your variables, your bases, and your exponents are, they still have to match in every way. So notice I have an a cubed and an a cubed in these two terms. And I have a b and a b and a c and a c. All of that has to match. If even one thing is different, for instance, if this were a 2 instead of a 3, they wouldn't match. If this side just so happened to not have the c here, they wouldn't match. They have to match in every way. All the same variables, all the same bases, all the same exponents. So look for that. But once you have that, the rest is easy. You just add together your two coefficients. So I've got negative 15 and a positive 1. When I add together negative 15 plus 1, you get negative 14. And then the rest of it just kind of carries down. A cubed BC. That's it. So these problems are often way simpler than they even appear at first. So that was our first rule, and that one was hopefully review. The next rule is what happens when we want to multiply together two bases. When we want to multiply together our bases, the rule we need to apply is add the exponents. Now that's a little weird, right? We're multiplying something. So notice here, we are multiplying two things together. But what we're going to do with the exponents is add them. So the first thing we need to make sure of is that our bases are matching. If they don't match, we're not allowed to put them together. It's kind of like terms. They have to match before we're allowed to add them. Well, here with multiplication, our bases must match before we're allowed to multiply them. So looking at example 1, I notice I have an n squared and an n to the 7th. My bases match. In both cases, my base is n. The exponents don't match, but that's okay. We don't need the exponents to match for multiplication. We just need the bases to match. So what we do is we rewrite our base, but we add together the exponents. So 2 plus 7 is going to be our new exponent. And hopefully that's fairly simple for us to calculate in our minds. 2 plus 7 gives us 9. So our answer would just be n to the 9th. Now this next thing I'm about to write up on the board, you do not need to write this down. I'm just showing you for demonstration purposes, but I do want you to look up at the screen and pay attention to this. So n squared times n to the 7th. I could rewrite n squared as n times n. We've already talked about what an exponent is. It's telling you to multiply n together 2 times. Well, n to the 7th is similar. That just tells us to multiply n together 7 times. So I'd have 7 more n's. Well, now look, if I multiply this times this, all I'm really looking at is 9 n's all multiplied together. That's n to the 9th. So really what I did was I took 2 n's and 7 more n's, and if I add all that up, it gives me 9 n's all multiplied together, which we would write as n to the 9th. So it makes sense I know it seems a little counterintuitive at first, but it makes sense why we add these together, why we add the exponents together. Even though we're multiplying our n's, we're basically adding in how many n's we have to our exponent. So you don't need to write any of this down. I'm going to erase it, in fact. I just wanted you to see why we have this really strange addition feature we're adding right in the middle of a multiplication problem. So let's do one that's a little more complicated. Notice in problem 2, I have bases that are different. I've got some x bases, but I also have some y bases. So the first thing I'm going to do is rewrite this. When you have multiplication, it doesn't matter what order things are in. So I'm going to rewrite it as x times x squared times y to the 5th times y to the 4th. So I just reordered it and I color-coded it. That just makes it easier for me to see kind of what's going to combine. My first x doesn't have an exponent, but here's where students tend to get tripped up. There is an exponent here. It's a 1. So when we go to use our rule to add our exponents, you should have a 1 plus 2. Many students forget that 1, and they just think their answer is x to the 2nd. But you have to have that 1 in there because that'll change it to a 3. All right, and our y's will be maybe a little easier, y to the 5 plus 4. And so these are going to simplify down to x cubed times y to the 9th. And that would be our answer to this problem, as simplified as we can get it. So moving on to number 3, the purpose of number 3 is just to show you that these parentheses just mean multiply. We are not trying to trick you with the parentheses. This just means 5x cubed times 6x to the 4th. So we could rewrite this as, let's do 5 times 6 times x cubed times x to the 4th. So the x cubed times x to the 4th part, that's where our new rule comes in. We'll have to add those exponents together, 3 plus 4. But this piece out in the front, the 5 times 6, do not let that confuse you. This is just 5 times 6. We've known our times tables since we were little kids. We could plug this into a calculator, or maybe we have it memorized. 5 times 6 is just 30. Don't let the fact that we're introducing all of these new rules about multiplication interfere with what you already know. You already know 5 times 6. Don't think, oh man, what rule do I apply here? No, you can just multiply 5 times 6. So this will be 30 x to the 7th. And that's our answer. Okay, one more. The purpose of number 4 is to throw a bunch of invisible stuff at you. The first of which is a 1 in front of this first a cubed. So the negative a cubed there could just as easily be written negative 1a cubed. And that's going to help us kind of figure out what needs to get multiplied together. Another thing that's missing here is this b doesn't have an exponent. So I'm going to write in a 1 on the b. And that's going to help me to not forget that later. So let's rearrange these. We'll put our numbers first. So I'll write negative 1 times 3. Then I'll do my a's. A cubed times a squared, and then I'll do my b's. B to the 1 times b to the 5. So we can simplify this part really easily. Negative 1 times 3, that's just negative 3. And we can simplify these a's, because they have a matching base, we can simplify these by adding together the exponents 3 plus 2. And we can simplify our b's, because they have the same base, by adding together 1 plus 5. So I hope you see how important it is to remember this 1, which you can trace all the way back to here. If you forget that 1, you'll end up with the wrong answer at the end, because we needed a 6 and not a 5. So just be cautious of little things like that. Sometimes taking just a moment up at the very first step to fill in some missing things can kind of save you toward the end of the problem. Okay, so if we're going to talk about multiplication, very soon after that, we'll be talking about division. They're kind of flip sides of the same coin. So the rules are very similar. Our bases must match, which was the same with our multiplication rule. Our bases must match, and instead of adding the exponents together, we subtract. The most important part of that subtraction, though, is you're subtracting the top minus the bottom. When I'm talking about top and bottom in the sense of a fraction. Remember, division is a fraction, top divided by bottom. So when we subtract the top exponent minus the bottom exponent. And that is probably the most common mistake I see on student work, at least in my past experience. So let's talk about a few of these examples. With example 1, we have x to the 5th, over x squared. Our bases match, they're both x's, so we can apply the quotient rule. When we do that, we rewrite our base and we subtract the exponents, top exponent minus bottom exponent. So that would be 5 minus 2. So 5 minus 2 gives us 3. Easy enough. That's our answer. Really quickly, I don't want you to write this down, but I do want you to watch. Watch me work this out on the board just real quick. I want to show you why this works out. If you have x to the 5th over x squared, another way to write x to the 5th is x times x times x times x times x, 5 times. And x squared can be rewritten as x multiplied to itself twice. Well, whenever you have a fraction with factors on top and factors on bottom that match each other, you can cancel them out. So 2 of these are going to cancel. Notice what happened here. We started with 5 on the top, but we took away 2 of them. We had 5 on the top, we took away 2. That's subtraction. Started with 5, take away 2, left with 3. So that's where the subtraction feature comes into the quotient rule. It's strange because we know we're dividing. That's what this means. We're dividing, but yet we end up subtracting, and it's because of that cancellation feature. So you don't have to do your problems that way, but I did want you to see that. All right, let's move on to number 2. And now you're going to need to start taking notes again. For number 2, hopefully this is pretty straightforward. We do have a matching base, so we subtract top exponent minus bottom exponent. And you'll have to be careful here. 4 minus 6 gives us a negative number. So we'll end up with m to the negative 2. Has anybody ever seen a negative exponent before? Show me your hands. Have you seen one of these before? Negative exponent? They're pretty rare. They do come up in algebra, but usually it's higher levels of algebra. We don't deal with them that much at this level, but we will be talking about these tomorrow. They have a special meaning, a special function, and we'll be discussing them tomorrow. So for right now, don't worry about what it means. Just know if you subtract the top exponent minus the bottom exponent, you could end up with a negative number. So in our next example, we have multiple bases floating around. Notice that these bases match my p to the 5th and p squared. And then these 2 bases match, the end of the 4th and the end of the 5th. So I'm going to have to basically treat this like 2 separate problems, 2 separate calculations. So let's start with the p's, since they come first in the fraction. We have to take our base to our top exponent minus bottom exponent. And then we'll have an n to the top exponent minus bottom exponent. So be careful as you do these. If you get your numbers mixed up, you'll get the wrong answer. Now let's simplify. The exponent for the variable p will be 5 minus 2, which is 3. And the exponent for the variable n will be 4 minus 5, which is negative 1. So again, we ended up with a negative exponent, but we'll talk more about those tomorrow. Example 4, we have a lot of different stuff going on. We've got some x's as bases, and we've got some y's as bases, but we also just have some plain numbers here. We have a 14 over a negative 7. Please don't let all these new rules confuse you. 14 divided by negative 7, that's just a numerical calculation that we all know how to do. We don't have to use any fancy rules, no exponent rules, nothing like that. 14 divided by negative 7, you can punch that into your calculator or your brain, and you'll just get negative 2. So don't be confused by stuff that you've known how to do since you were a child. Okay, we are throwing new rules at you, but it's new rules for exponents. It's not new rules for dividing. So this becomes just negative 2. Now let's look at the x's. We have x to the 5th over x to the 5th. So when we write our base, x, we subtract top exponent minus bottom exponent. So that will be 5 minus 5. Then let's look at the y's. We'll have y to the 3 minus 2. So if we rewrite all of this, we end up with x to the 0 and y to the 1. That x to the 0 is also a little weird. I'm going to make another note. We will revisit these tomorrow. So negative exponents and 0 exponents behave a little differently than the rest of the exponents. So we're going to have to talk about those with some of our skills practice tomorrow. But for right now, we'll just leave our answer like this. You don't need the 1 on the y to the first power. It can be there. It's not wrong if it's there, but you could also erase it if you so choose. And we have one more rule to talk about. This one's not too bad though. So we've talked about what we're doing when we're multiplying, well, when we're adding, subtracting, when we're multiplying, and when we're dividing. The next step is when we have exponents on exponents. It's like exponentception or something. So we're going to have exponents all over the place in these problems. The rule is when you have one base with multiple exponents, you will multiply the exponents together. That's our rule. So we'll just talk about this through example. In example 1, we have a single base. Our base is n. That base has multiple exponents. It's n squared to the 7th power. The way we simplify these is we multiply those exponents together. So we would rewrite this as n to the 2 times 7, multiplication. So that, of course, would simplify n to the 14. Number 2 has an extra step going on. First of all, I'm just going to look at the first piece. X squared to the 3rd. Well, that's a single base with multiple exponents. So we're going to rewrite this as x to the 2 times 3 power. But then we have another totally separate base with 2 exponents on it. We're going to do something very similar here. This will be x to the 3 times 3. So when we simplify these, we get x to the 6th times x to the 9th. And now what? Now we're looking at an expression where there's no longer a single base with multiple exponents. Now we have 2 different bases, but our bases match. And when our bases match, we are allowed to multiply these together. When we do, what do we do with our exponents? Add them. Yeah, we just learned that rule a couple minutes ago. We can add these exponents together. So we will combine these by calling this an x to the 6 plus 9, which is x to the 15. So this problem involved multiple rules. Sometimes you're going to use multiple rules in the same problem to simplify something. Number 3 is going to have something a little bit new. Notice this exponent on the outside. Remember that exponents affect whatever they're directly touching. In this case, that's a giant set of parentheses with a whole bunch of stuff inside. In order for this exponent, to be properly applied, the first thing we have to do is distribute that outer exponent in to every single piece on the inside. So that 2 applies to everything inside those parentheses, every single one of those bases. So what we're going to do is we're going to rewrite each one of those bases in parentheses with a new exponent of 2 on the outside. So I start with the 5, and I write 5 squared. And then I do the x cubed, and I write x cubed squared. And then we do y to the 5th. We write y to the 5th squared. And then we've got z squared squared. So all 4 of the bases that were on the inside now have to have that 2 as an exponent. Some of these are pretty easy to simplify. For instance, 5 squared, that's just a numerical calculation. 5 times 5, that'll give us 25. The next piece is a base with 2 exponents. So we can rewrite this by multiplying those exponents together. The piece after that is another base with 2 exponents. So we'll rewrite that as y to the 5 times 2. Come on. And then finally, we have our z to the 2 times 2. So our ultimate answer ends up being 25 x to the 6th, y to the 10th, z to the 4th. One more problem. Our last problem is a little bit tricky because there is some missing information here. First of all, we have a negative a cubed, but there's no number next to that negative. So it's usually pretty helpful, and I find it very helpful to imagine that there's a 1 there. I'm going to write that in a different color. So I'm going to imagine that's a negative 1. Okay, students, we were kind of in the middle of example 4. I will recap what I'd already said. We have some missing information here. You often have to add 1s in where 1s belong just to remember that they're there. So I'm going to think of this as a negative 1 a cubed. But also, look at that b. That b should be a b to the 1. We don't always write that 1. In fact, we very rarely do, but it might be helpful to us to think of that as a b to the 1st power there inside the parentheses. You don't have to do it this way, but sometimes that can be helpful. So what we're going to do with that is we're going to start with the 4. We need to take this 4 that's on the outside and distribute it in to every single base on the inside. So that means we'll have a negative 1 to the 4th, an a cubed to the 4th, and a b to the 1st to the 4th. With the first piece, negative 1 to the 4th, that's the same as negative 1 times negative 1 times negative 1 times negative 1. So it doesn't take a calculator to figure out that when we multiply all of these together, all of those negatives are going to eventually end up canceling. And we'll just have 1 times 1 times 1 times 1, which of course is just 1. So when we take this negative 1 to the 4th power, we end up with a positive 1. Then our a has 2 exponents, 3 and 4. So we need to multiply those together. And then our b also has 2 exponents, 1, what is up? And 4, so we'll multiply those together as well. So we can simplify this down quite a bit. We don't need to write the 1 in the front. You can have it. It's not wrong if it's there. but the A becomes A to the 12th, and B becomes B to the 4th. So you might notice at this point, it wasn't necessarily mandatory that we write this one in, but I find that it does help me just kind of stay organized. So I recommend it. All right, so that was the end of today's guided notes. If you are virtual at home, make sure you snap a picture of this page and submit it on Canvas under the guided notes assignment today.